talk about the boundary layer equations. Okay. So let's imagine that we have a very complicated situation. We have thermal boundary layer, velocity boundary layer, and mass boundary layer, all of them existing at the same time. So basically, we need to write down coupled differential equation for conservation of mass, energy balance, and momentum balance. So again, we have done conservation of mass analysis in fluids multiple times. So in 2D, so we have mass coming in from X direction, mass leaving out in X direction, mass coming in Y direction, mass leaving out in Y direction. So if this is a steady state process, the difference between these, the contribution of the summation of the contributions should be 0. And then you'll be obtaining this equation. And this equation, we called it as continuity equation. And so you can also do the similar analysis for the momentum balance. So again, I'm not going to redrive this equation. I'm just going to highlight this momentum equation in X direction. And when you are dealing with momentum equation, you need to write this down in Y direction as well. So this is the equation in X direction. A very similar equation in Y direction exists also. And then you also need to think about energy, conservation of energy. In this case, we need to think about internal energy coming into the system, internal energy leaving out of the system. Then you'll also have viscous dissipations that are going to cause some energy processes here. So, and this is the energy balance. When you couple fluid motion with internal energy balance. And then, so again, these equations, these are all coupled differential equations. We already wrote down 3 of these. These are very difficult to solve if you don't make any assumptions. So we need to realize the following assumptions. So for the boundary layer, as I mentioned, they are very thin. So the thickness of the boundary layer, if this is delta, if this is L, usually delta is much smaller than L compared to the length scale of the object. So that means the velocity, let's say U is the velocity in X direction, V is the velocity in Y direction. The velocity in X direction for the laminar region is much greater than velocity in Y direction. So, and if the velocity is, if this is the first piece of information, if you want to compare delta U by delta Y versus delta U by delta X. So change in velocity along the Y direction. So the velocity is rapidly changing from here, let's say 0 to 99 in a very small section. Delta Y is small, delta U is the same. That means this derivative, delta du by dy, is much greater than du by dx. And since U is much greater than V, du by dy is much greater than dv by by, and then we can conclude that this will be the relative magnitudes of the velocity. Same story holds for the temperature. So temperature is very rapidly changing in y direction in a very small y value. So this means this derivative is dt by dy is much greater than dt by dx. Same story for the concentration. And then we have the definition of the shear stress, which is mu times du by dy. And again, we neglected dv by dx because it is small compared to du by dy. So now then you can do normalization. So you can normalize x with respect to length, y with respect to length, velocity with respect to incoming stream velocity, incoming with stream velocity, u infinity or v, we can call it either way, capital V. So you normalize the other velocity, the velocity in y direction with the same velocity, upstream velocity. So you normalize temperature with Ts minus T infinity, concentration by Ca infinity minus Cas. So now after you go through a lot of manipulation and algebraic equations, you'll be obtaining a transport equation in terms of non-dimensional numbers. So you'll have velocity transport equation, thermal transport equation and concentration transport equations. And the boundary conditions will be, so the velocity will be 0 at the wall, and velocity very far away from the wall will be stream velocity, and temperature will be equal to the wall temperature for the fluid at y equal to 0, and infinitely away from the object you will have temperature equal to upcoming stream temperature. So so if you pay attention to these equations, we non-dimensionalize these equations, and so we obtain Reynolds number here. This is dimensionless number here. And in thermal energy balance, we have Reynolds number and Prandtl number. And this is another dimensionless number I'm going to define now. So let's talk about the significance of these dimensionless numbers. The Reynolds number is basically the ratio of inertial forces to viscous forces. And we have seen this, we have analyzed this in fluids in quite detail. So it's defined as rho v L over mu. And the Prandtl number is defined as the ratio of the momentum to thermal diffusivity. It is defined as Cp mu over K. Cp mu over K, this is the Prandtl number. And analogous equation is basically, an analogous dimensionless number is the Schmidt number, which is defined as which is defined as the effectiveness of momentum to mass transfer diffusion. Okay. So here in this table, I would like to just go over the dimensionless number. So most important dimensionless number in this course. So we have talked about Biot number in the context of lump capacitance method and special effect analysis in time-dependent problems. So another important number is called CF. This is the coefficient of friction. It is defined as shear stress divided by rho v squared over 2. We talk about Fourier number. This is dimensionless time. So we talk about this in the context of, again, lump capacitance method and special effects analysis. So we are going to talk about Colburn J factor, which is called JH. This is another dimensionless number. It's a combination of two dimensionless numbers, Stanton number and Prandtl number. So we will be talking about the Nusselt number. This is the most important number from now on. This is going to allow us to find H. Okay, Kf is the fluid thermal conductivity. L is the length. So this is the number that we will be using in chapter 7, 8, 9, and 10 to calculate H values. So we'll have a lot of empirical equations which will be giving us the Nusselt number, and then we'll be calculating H from the Nusselt number. And we have Prandtl number. This is another important number. This is the ratio of the momentum to thermal diffusivity. And Schmidt number, analogous of that in mass. So we'll be using the mass in mass transfer. Instead of Prandtl number, you'll be dealing with Schmidt number. And obviously Reynolds number is always important. So now let's focus on the most important dimensionless number, which is Nusselt number. So the Nusselt number is defined as HL over K fluid. This is K fluid. So, and if you compare the form of the equation with the Nusselt number versus Biot number, so both of them have HL over K, but for Nusselt number it is fluid, for the Biot number it's for the solid. Okay, so this is an important distinction. And you can also define an average Nusselt number instead of a local Nusselt number. In this case, you'll be replacing H local with H average. And in most cases, the Nusselt number will be function of two dimensionless number, Reynolds number and Prandtl number. So we will have a lot of empirical equations that will allow us to calculate the average Nusselt number from the Reynolds number and Prandtl number. And if you are interested in finding the local Nusselt number, then it will depend on at what point you are trying to evaluate the Nusselt number, and it will be involving position. Okay, And after you have the Nusselt number, again, you go back and you find H. So that's the idea. So same story holds for the Sherwood number, and this is in mass transfer. So again, yeah, it is very similar. In this case, you will be estimating the Sherwood number from Reynolds number and Schmidt number instead of Prandtl number. So Prandtl number will be replaced by Schmidt number, but all other principles are the same. The logic is the same. So as long as you understand how to calculate Nusselt number and how to find local and average heat transfer coefficient, convective heat transfer coefficients, the same story holds in mass transfer as well. This table basically summarizes key equations here. So in fluid flow, we are interested in velocity profile, and velocity. The velocity depends on position in x and y, Reynolds number, and pressure gradient. And the most important dimensionless number in fluid flow is the coefficient of friction. So it is a function of Reynolds number. In the case of heat transfer, we have temperature. Temperature will depend on position, Reynolds number and Prandtl number, and obviously delta P, because U star changes T star. So the velocity profile changes T star. If the velocity profile depends on these variables, the temperature has to depend on these variables. But on top of that, we have also now the Prandtl number that is important. And in this case, we'll be having Nusselt number. We'll be calculating the Nusselt number, and from Reynolds number and Prandtl number. And if it is local, it will depend on position. If it is average, it is going to only depend on the Reynolds number for the whole system and the Prandtl number. And finally, there is one more equation that I want to mention. This is called Reynolds analogy. So this is the very first equation that will allow us to calculate convective heat transfer coefficient from the flow conditions. Okay. So in chapter 7 and 8, we'll be dealing with a lot of different types of empirical equation. This is the very first one of this equation. It's sometimes called its modified Reynolds equation, or Chilton-Colburn analogy. So equation is straightforward. It is telling us the coefficient of friction divided by 2 is equal to product of Prandtl number, product of Stanton number multiplied by Prandtl number to the 2/3 power. Alternatively, we can say the Colburn J factor is equal to Stanton number multiplied by Prandtl number to the 2/3. So if you are trying to find H using this equation, so you need to know all of the properties for the fluid. You need to know the heat capacity, viscosity, thermal conductivity, and you need to know the velocity of the fluid. You need to know density of the fluid. So ultimately, H is hidden in Stanton number. So you are trying to find Stanton number, which is JH over Prandtl number to the 2/3 power. And Prandtl number, all of this number will be calculated from this equation, CF over 2. Prandtl number's definition is given here. So if you know the shear stress, if you know the velocity, and all the properties of the fluid, you can estimate H. So you don't need to know H value. You can estimate it based on the flow conditions and properties of the fluid. So that is the main idea behind these kind of analogies. And again, this is the most simple case. It's for the flow, for the laminar flow or turbulent flow over a plate. So this equation is valid when the Prandtl number is in this range.